Okay, now we're going to move into the next realm. I've got a little problem for you in Roman numeral 2. Pretend that I'm teaching statistics to 20 students at MBC and 20 students at JMU this summer. I'm not, but pretend that. I want to get their attitudes towards statistics, so I sample 3 students in each class. I use a 5-point scale, with 5 being a very positive rating, 1 being a very negative rating, and see what their attitudes are about statistics. Now notice here I would not do a chi-square here. Can you figure out why I wouldn't do a chi-square here? Because we're not looking at frequency anymore, how many like and dislike. We're on a rating scale, so a different type of statistic would be appropriate here. None of the ones I mentioned in the discussion board situation though. So going back to our story here, let's say the data set 1 is from Mary Baldwin College. I have 3 scores there, 2, 3, and 4. Data set from the JMU sample, 1, 3, and 5. But notice there's something very, very important here. These 3 scores are now not representing everybody. They're just representing 3 people in each case out of 20. So this is a sample situation now. And most of the time in psychology we're dealing with sample situations. So I could get, to describe these data sets, I could get measures of central tendency. Do you remember the 3 ones? Mean, median, and mode. Mean is most often used, and it would be what in each case? 3 in each case, so it looks like these data sets in terms of central tendency have the same mean. What about dispersion? Do you remember the 3 that are most often used? Well, we could start off with deviations from the mean, right? That's not really used very much because the deviations from the mean always equals 0. But notice some of my symbols are a little different here. Instead of going x minus mu, I did x minus m. Do you know why I used an m instead of a mu? Well, you use alphabetic letters like x's and m's when you're dealing with samples. I'm not dealing with a population anymore, so I can't use mu. So the deviations in the mean, that's always going to equal 0. 2 minus 3 plus 3 minus 3 plus 4 minus 3, then 1 minus 3 plus 3 minus 3 plus 5 minus 3. The sum of the deviations in the mean always equals 0. So the 3 most often used ones, one is called the sum of the square deviations, the sum of squares. Can you figure that out in this particular case? 3 consecutive numbers for Mary Baldwin College, 2, 3, and 4. Sums of squares are always 2. For 1, 3, and 5, it would be 1 minus 3 quantity squared plus 3 minus 3 quantity squared plus 5 minus 3 quantity squared. So the sums of squares would be 8 there. So it looks like, once again, there's more dispersion for the JMU data set. Now, the variance. The variance is going to be a little bit unique here. There's a little bit change in the formula for the variance situation here. The variance in the population situation above, it was the sums of squares divided by n. But now, there's a little correction for this. It's the sums of squares divided by n minus 1. And there is a picture in your book. See if I can find the right page. Got to put my glasses on here. That explains the logic and reasoning behind this. It's a good picture. Page 114. On page 114 it shows a little picture there, but let me just share the verbal with you first. The reason there's this n minus 1 has to deal with the fact that we're working with a sample here. And the key idea is that if you have 20 scores in a group and you only pick out 3, most of the time you're going to tend to pick 3 scores from the middle. And those 3 scores are going to underestimate the dispersion of the population. If you look at the X's there that are picked out in figure 4.4, notice most of the X's, the scores that are being picked out, are in the middle. So when we use a sample and we're trying to figure out stuff about a population, many times we underestimate the variability. So now in our formula, we have to correct for that, and we do this n-1 situation. Notice also that the symbol for variance is not sigma squared, but it's s squared, because this is a sample and not a population. So if we were to work with the first situation, the 2, 3, 4, the sums of squares, you might remember being 2. But then we do n-1, so there are 3 scores, so the variance would actually be 1. And then we take the square root of the variance for the standard deviation s, that would also be 1. And so the variance and standard d are much larger now. In the case above, the variance was 2/3, because the 3 scores that were being represented there were actually the 3 scores from the population. Now the 3 scores that we have are really just 3 scores from a group of 20. So we do this correction when it's a sample situation. And the other one, 1, 3, and 5, the sums of squares was 8. And instead of doing 8 divided by 3, now it would be 8 divided by 2. So the variance is larger now at 4. The square root of 4 for the standard D is 2. So hopefully that makes some sense. You can certainly read the book a little more about this as well. But when we use a sample, we tend to underestimate dispersion. So the n-1 is used as a correction when we're dealing with a sample situation. So your homework in this particular situation, what I'd like you to do is consider the following data sets. Mary Baldwin data set of 0, 3, and 6. A JMU data set of 2, 3, and 4. What I'd like you to do is the computations for central tendency, the mean, and dispersion first, as if these are all the scores that we have, that they're coming from a population. And in the second situation, pretend that they're coming from samples, the 6 scores. Compute the key things for sums of squares, variance, and standard D, and if there are differences in those numbers between the groups and between doing them as populations and samples, share what those differences are and why they're actually occurring. All right, that'll do it for this one. Thank you all very much. Bye-bye.